All right, now it's time for an example. So let's take a piece of aluminum. We have a piece of aluminum, and if you look up in the textbook, you'll find that aluminum has a work function of 5.08 electron volts. That means that you need photons that have an energy greater than 4.08 electron volts to actually create a current. Okay, so remember that the electrons are going to absorb the energy of the photon, and if all they had was that much energy, the photons, and then the electrons absorb it, well, that's not quite enough to produce a current. It has to be greater than that. All right. So the first thing I want to do is figure out the cutoff frequency. So what frequency of light or electromagnetic wave? So what frequency of electromagnetic wave and the corresponding wavelength will, if you exceed that frequency, you'll get, you can get a current, and if you, well, if you don't exceed it, then you don't have a current. So that's the first thing I want to figure out here. All right. If I were to just draw that graph real quick again. The width this is what Ke max and frequency. Here's 0. That's the frequency we're looking for. We're looking for that frequency and the corresponding wavelength right here. Now remember that your governing equation for this is Ke max equals the energy of the photon that's going to be absorbed minus the work function. And the Ke max is what's left over. Assuming that the photon has more energy and it's completely absorbed, it has more energy than the work function, the energy necessary to kick the electron off of the metal in the first place. Okay, that's the leftover energy. At the cutoff, it's 0. So 0 equals HFC minus phi, or in other words, phi, the work function, equals HFC. Now I'm going to go ahead and solve for the wavelength first. The reason why is it's just easier to deal with wavelengths because we know HC, this you don't have to do it in this order, but we know that HC is 1240. I like that number. It's an easy number. This is 4.08, and that's 1240 electron volt nanometers, right? So let's solve for theta C. All right, multiply both sides by theta C. Get it, I mean, sorry, not theta C, but lambda C, excuse me, cutoff wavelength. This is 1240. And divide by the work function, which is that 4.08. Excuse me. That comes out to be 304 nanometers. What does that mean? It means that any wavelengths, remember wavelength and frequency are inversely proportional. So any wavelength that is longer than that, we're not going to get any photoelectric effect. Any wavelength that's shorter, which would correspond to a higher frequency, would give us a photoelectric effect. Now let's go ahead and calculate the frequency. Again, I could have done it here, but I need to come up with the frequency in hertz. There's a couple different ways to do that. We could have done it here, but you could also do this. You know that C equals F lambda, and so in this case, that's going to be C all over lambda C. Now you have to be careful, be sure that you remain in meters, because this is in meters per second, not nanometers per second. So 3 times 10 to the 8 meters per second has to be divided by 304 times 10 to the negative 9 meters, because nano is 10 to the negative 9 meters. You have to mean meters. Or 304 times 10 to the negative 9 is the same as 3.04 times 10 to the negative 7 meters, either one. And that comes out to be, let me see, I've done this somewhere in my missing notes. It comes out to be 9.87 times 10 to the 14 9.87 times 10 to the 14 hertz. You'll notice that most of your frequencies near the visible spectrum and in the visible spectrum are in the 10 to the 14 range. That's 100 trillion range, all right? A trillion being 10 to the 12. This is in the 100 trillion range. Oscillations per second. That's pretty rapid. Okay, there's your frequency. There's your cutoff frequency. Okay, continuing on. Let's find, let's say that ultraviolet light has a wavelength of 250 nanometers, which is shorter than that, higher frequency than that, because the wavelength is shorter than that. So that's going to produce a current, right? So find the energy of a single photon to start off with. Let me erase this.